Hey and welcome. Today we will solve special positions in a binary matrix interview question, so let's get into it. Here is the first example. As you can see, we have this binary matrix, and by that it means a matrix that only holds zeros and ones. And the point is, we might find a cell that holds number 1 as value, but that might be the only one in its row and column, like this blue one here. There's no other 1 in that row or column. So we should only return 1 as result, indicating that we found one match for that condition. Second example. As you can see, all 1s here satisfy the condition of no other 1s in their row or column, so we will return 3 as result. Let's see how we are going to solve this problem. As of a brute force solution, we can iterate over our matrix to access each cell. Then for each of them that contains 1, we can once look for its adjacent cells in its row, and next look for its adjacent cells in its column. But this is going to be a hassle in terms of time complexity and runtime, because we are already having O of n by m time complexity only for reaching into cells. And from there on, doing 2 other ON loops just for scanning all cells in row and column of that specific cell that we are on sounds not that much efficient. This question has a cool trick to solve it. Let's see it. The key here is we might look into cells containing 1 from frequency point of view in each row and column. Let's say in our iteration over cells, what if we have 2 separate arrays? That first one will be as same lengths as rows in our matrix, and it will be responsible for frequency of 1 appearances in each row. And same goes for columns as well. The second array will be the same lengths of our matrix width or column count and hold the frequency of 1s we see in every column. And just as a side note here, a matrix can be like this or this one here. That is why I make this very clear about frequency maps being as same as lengths as rows or columns. Okay, but why do we need this frequency arrays? The answer is simple. Now, if we do another iteration over our matrix, at any cell that we see a number 1, if we check the frequency of that one is also 1 from row and column perspective, that would mean that we found a hit there. And the proof will be our frequency maps. Because in that column or index, we only going to have 1. And there's no other 1s in that coordinate. Now, I'm sure you have a pretty much clear picture of how pre-computing frequencies can help us to get into our answer. With that being clarified, let's jump into the code to implement this solution. Here we are in Leetcode. Initially, we need to store the widths and lengths of our matrix in separate variables because we are going to use them multiple times. Then we will create our frequency arrays for rows and columns, and initially they will be filled with zeros. I'll get back to you why we need to fill them and why 0 in a second. Now it's time for our first iteration over matrix. Just a simple double for loop. But keep in mind that we will visit every cell only once. We should not worry about having O of n in power of 2 time complexity for it. Within this iteration, we will check if the value of the cell is 1, because if so, we might increment the frequency of that indices in our respective frequency arrays. And here is why we filled and put zeros in our frequency arrays initially. Because if we didn't, at here, when JavaScript tried to increment the value, it would have found nothing here within the frequency maps at that specific index. Now we are stepping into the second part of our function where we cook the result. So we will initiate the result variable as 0, which will be the number of matched 1s with the criteria that questions asked for. Then another iteration over matrix. This time within this iteration, first we need to check if cell value is 1. Then we might check if that specific row index and call index from frequency maps gives us also 1, because again, if our frequency maps indicates that there's only one cell containing value number 1 in that coordinate row and columns, then we have a match there, and we might increment the result variable for that. And finally, after our second iteration over matrix, we are going to return the result variable. Now if I run this, test cases are passing, and if I submit, we are in a good shape here. Now let's jump into the slides for time and space complexity analysis. So the time complexity will be O of 2n by m because we will iterate all cells in matrix 2 times. But we will ignore the constant value of 2 since they does not make any difference in terms of time complexity. So it will be O of n times m eventually. And the space complexity will be O of n plus m because we store 2 frequency arrays which are as same lengths as width or height of our matrix. And please note that a matrix could be 3 by 3 or 4 by 3. So the frequency arrays will have different lengths. That is why we sum them here. So that was it for this video. Thanks for watching, and please leave a like, comment, and subscribe to the channel. I will put a few more links about different playlists in the description for you to check it out. And finally, hope you enjoyed this video and stay tuned for the next one.